Welcome to Introduction to Algebra Tiles for the 7th through 12th grade math classroom. I'm Sarah Fleischman. I'm one of the consultants at CISA 6.
And I'm Chris Meffert. I'm Sarah's partner in the Math Center.
We're really happy you could join us today. Our goal for this webinar is to introduce algebra tiles as a concrete representation of algebraic concepts. And Chris and I are so excited about this today because we have seen algebra tiles change classrooms and change math students as they use them. So I'm going to let you share your screen, Chris, and we'll get started.
All right. Can you see my screen?
Yes.
Great. Okay, so I brought in the cast of characters that we have here. These are our algebra tiles that we're going to be using today. And if I flip each one over, I can see they all have a red side. This signifies the negative of the piece. So I'll set these two aside for a second, and we're going to talk about this guy right here. So algebra tiles are based on an area model. Okay, so I'm just going to draw out the area of this shape right now, and it's a 1 by 1 square. I have a length and a height of 1 on each side. So we know that in area, length times width, 1 times 1 equals 1. So this signifies 1. Simply 2, okay? If I bring this guy in, this is the opposite of that. So this equals a negative 1. Okay, so let me introduce you to this one. And let's take a peek at what we have going on here. So if I bring in one of these, and I forgot this, we're going to call this a unit. So if I bring this unit in and I compare it to this piece right here, I can see that this side is the same. So we're going to call that 1. And then if I try to line up a few of these against that other edge, I get about 5, but a little more than 5. I'm not exactly sure what that is. So that's going to become our variable. We're going to call that edge x. And this whole piece becomes our x. Okay? Opposite, negative x. Let's look at this one. And I bet you can predict what I'm going to say here. If I take our x and I compare it to this piece, I can see that this edge is x. And I can see that this edge is x. So this, x times x, is x squared. And the opposite of that equals negative x squared. Okay, so those are our players. And I'm going to keep these two guys on here for just a second. Now let's look at these two. We're going to talk about when we have a positive number and we have a negative number. The same positive, the same negative, they equal 0. So let me just show you that on a number line real quick. If I have, say I have a negative 1, and I add to it a positive 1, it's 0. These create 0. So we're going to call these a 0 pair. If I have 2, and I have the opposite of 2, this all equals 0. Okay, so keep that in mind because we're going to be using these 0 pairs quite a bit. So let's look at adding some integers. We're going to start very simply here. Let's try this one. Very simple problem, 5 plus 3. We put out 5 positives. And I put out 3 positives. And I can very easily see that 5 plus 3 is a total of 8. Let's try this one. I have a positive 2 and a negative 6. Okay, so let's take that idea of that 0 pair. Let's line those up. Those equal 0, so I have 4 negatives left. Okay, and when you're doing integers, you don't need the algebra tiles. You can use those two-sided coins that are red and yellow on each side. Okay, let's move into subtraction of integers. Let's try this one. So I have a positive 4. And I'll put out a negative 7. Okay. I'm going to line up what I can zero pair here, and I can see that I have negative 3 left. Let's try this one. This is a problem that could send kids into fits. Like this, a lot of this is, you know, we got a lot of minus signs going in here. I want to bring in, what is the definition of that symbol right there? And we know in early elementary years that we can think of it as subtract, we can think of it as take away, minus, maybe remove even. As we get into 6th and 7th grade, we bring in the definition of a negative number for that symbol. That means negative. But let's also think of it as opposite, okay? So that symbol can mean opposite. So I'm going to build negative 6. Okay, and I have negative 6, and I'm going to look at this as, I'm going to take away that minus sign in between there, and I'm going to build negative 2. Okay, and using that definition of opposite, this problem says I have negative 6, and I want the opposite of negative 2. What is the opposite of negative 2? It's a positive 2. So I can line up in zero pair, and I have negative 4 left. Sarah, do you have another way that you think about this problem?
Well, we could model that another way. We have negative 6. If instead of thinking of that as opposite, but I really think that thinking the way you modeled it, thinking the opposite of negative 2 is so life-changing and important. I loved what you did. There would be another way to model it. We could say negative 6, take away negative 2. So Chris, you could just reach in and take away negative 2. And we would see that it is negative 4.
Okay, because if you remember, that symbol can be take away, it can be remove. We need to get flexible with what that symbol means. Okay, let's look at this one. Actually, let's move on. Let's go to building. Let's try this one. Let's just build some simple expressions. X plus 3. Let's try this one. 4x and a negative 5 or minus 5. 4x minus 5.
So what's so cool about these algebra tiles is they are a concrete way to learn algebra. They are a manipulative, something that the students can actually touch. I know when I've seen students work with these through the years, they start at this stage, but they do often move into the next stage, which is representing the manipulative with a drawing. And yes, exactly like that, Chris, where after some time of working with the tiles, we might move to the point where we don't have the tiles out and we are drawing what we picture in our head instead. So thank you for sharing that. But absolutely love what you're doing in the concrete tiles, Chris.
Okay, did you notice here? Take a look at this. I have 4x minus 5, and I have 4x and the opposite of 5. Exactly the same, but it really becomes clear when I can build it with a concrete model. We're going to move to some simplifying expressions. Let's try this one. So I'm going to build it. 4x plus 8 plus 8 minus 3x. Okay. 4, 6, 7, 8. Okay, so I need to just combine like terms here. Pretty easy to see what the like terms are, right? And then I'm going to zero pair. So I can zero pair this, I can zero pair this, and zero pair this. So simplified, x equals 8. Let's try one more. 3x plus 2 minus 4x minus 5. Very easy to see what my like terms are. Combine them. Zero pair. And zero pair here. And I get negative x equals negative 3.
Negative x plus negative 3.
Sorry. Okay. Let's look at some equations. And we are moving through this very quickly. Warp speed, okay? We just wanted, remember this is an introduction to algebra tiles, so we wanted to give you the opportunity to see the broad range and the broad scope that you can use these. Okay, so I have this equation, and I'm going to put it right there, and you can see I have a line on my mat here. So I'm going to build x minus 2 on one side, and then I'm going to put 7 on the other. Okay, we need to remember a couple things about solving equations, and that is one, we need to keep it balanced on each side of the equal sign. So whatever we do to one side, we have to do to the other side. And we're trying to isolate that variable. We're trying to get the variable by itself so we can identify what the value of that variable is. So how would I get these off of this side? Well, let's bring in the idea of that zero pair. I can put 2 positives there and this becomes 0, but if I do that to this side, I have to do it to the other side. Okay, these 0 pair out and I can quickly see that x equals 9. Okay. Try this one. 3x minus 2 equals 4. So again, we need to balance out. I want to get rid of these from this side, and if I bring in 2 to make a 0 pair here, I have to bring in 2 to this side. I can 0 pair, and then look at this. I have 3 x's here, but my goal is to figure out what 1x would be. So I can take what I have here and divide it up equally between each x, and I can see very quickly that 1x equals 2.
When I learned algebra as a kid, I learned formulas and rules and do this, do that, and it was a lot for me. Since seeing algebra tiles as an adult and working with them for the last 5 to 10 years, my brain now thinks in pictures of algebra tiles rather than in sets of rules. And that's so exciting to me. I just can't say enough about this conceptual, how these algebra tiles build conceptual understanding.
Okay, so let's try a word problem. One of the things that I find really important, and quite often it's a missed part, is actually getting students to understand what the variable is, assigning something to that variable and assigning something to those units. What is it? What are they? They're not just random numbers. So let's take a look at this problem. A total of 8 students from 2 schools attended a mathematics tournament. 1 student from Jefferson High rode a bicycle. The rest were transported in a car. 3 students from Lincoln Middle School rode bicycles. The rest were transported in a car. If all the cars transported the same number of students, how many students rode in each car? So our end game here, the answer that we're trying to get is how many students rode in each car? So what do we know about this problem? Sarah, what do you think?
Well, I see that there was 1 student from Jefferson High who rode his bike or her bike. So I'd like to put out 1 unit to represent that Jefferson High student. And I also see that there were 3 students from Lincoln Middle School who rode bicycles. So I'd like to put out 3 to represent those 3 students. I also noticed that we don't know how many kids were in the cars, but the cars held the same number of people. So because we don't know, would be our variable. So I'm thinking we'd like, yep, an X for each school. All of this, the first sentence says it's a total of 8. So 2x plus 4 would equal 8 total.
So I can put 8 on this side. Okay. Okay, so what do? We've just finished doing solving some linear equations, so we need to use the same balanced equation here, and we're trying to isolate the variable. So how do I get these out? I bring in 0 pairs. And if I do that to one side, I have to do it to the other side. Okay. 0 pair this out. I now have my x's by themselves, and I'm going to 0 pair out these. And I end up with this. So I have 2x equals 4. And I can just simply distribute those, divide them up between the 2 x's. So this is the representation of a car. X is how many students are in a car. 2 students are riding in each car. That's fun. Okay.
Wouldn't it be great if all of the problems we did were real life, real world problems? I love that one.
Let's add some polynomials. So I'm going to build it. 2x squared plus 3x plus 5. Okay, I'm adding it together, so let's build the next one. X squared minus 2x, sorry, 2 x's.
And that should be minus 2, so we'd want those to be negative x's.
Okay, so this can look a little intimidating, but when I see this, I can actually visually see there's a lot of like terms here. So I'm going to combine my like terms. And I'm going to 0 pair, can't 0 pair anything here, but I can 0 pair 2 of these. And I can 0 pair 3 of these. So I should end up with 3x squared plus x plus 2. Let's try this one. 3x squared plus 2x minus 4. You see a plus sign there, so I'm going to build the next one. Negative 2x squared plus x minus 3. Once again, combine my like terms. Zero pair, I can see I can zero pair two of these x squareds. And I should end up with x squared plus 3x minus 7.
And as you mentioned before, Chris, we are really moving at warp speed, and we're just doing a couple of each different kind of problem. In the classroom, we would spend a lot of time and have the kids working through lots of different problems.
So we're going to work on subtracting polynomials now. So I have 2x squared plus 4 minus 5.
And there's that minus sign because we're subtracting. So we can think of that as subtraction, removal, negative, opposite, take away. I'd like to think of it as take away. And let's just see if we can take away an x squared. Let's see if we can take away 2x. And let's see if we can take away negative 3.
X squared plus 2x minus 2.
And thinking of it as take away worked really nicely in this example. It won't work in all the examples. Let's check this one out.
2x squared, 2x minus 1.
So if I was going to think about removal or take away in this example, I could take away an x squared. I could take away an x, but I wouldn't be able to take away a positive 3.
But you can take away a negative x.
Oh, and I can't take away a negative x. You're right. So in this case, thinking of this as removal or subtraction, takeaway isn't going, sorry, not subtraction, removal or takeaway isn't going to work. We may have to think of this one as the opposite of. So let's try to model this one as thinking the opposite of x squared minus x.
Set that aside for a minute. I'm going to set aside that symbol, and I'm just going to build what I have here. X squared, a negative x, and a positive 3. Okay, now I'm going to bring the symbol back, and I'm going to use this as the opposite. So I need the opposite of x squared. That's negative x squared. I need the opposite of negative x. That's a positive x. And I need the opposite of 3, which is negative 3. Now I can combine my like pairs, or my like terms, sorry, and I can zero pair. And I should have x squared, a 3x, and a negative 4. Let's move into multiplying and using the distributive property. So when I look at this, I see multiplication. I see 2 times 4x plus 1. And we know multiplication can be considered groups of. So I could build 4x plus 1. And this is telling me that I need 2 groups of that. So I'm just going to build it again. And I'm going to combine my like terms. So 4x, 2 groups of 4x plus 1 is 8x plus 2. Okay, let's look at this one. Okay, well, I know I have to multiply these, but the variables in there are confusing me a little bit. I'm not sure, but I can build this. So let's take a look at what this would look like. One of my factors is 3x.
So you're building it as an array.
Yep. Okay, an area model. So now I can multiply 1x times 1x, and I get a positive x squared. 1x times 1x, x squared. X times x, x squared. So my answer comes right here, 3x squared. How about this one? 2x times 2x. Build it again. And my answer comes right here, 4x squared.
It's great that we could just see that. We didn't have to know a formula or a rule.
All right, let's multiply some polynomials. So I'm going to build those factors. X minus 1, and I'm going to put it into the area model again. And on this edge of my model, I'm going to do x minus 4.
So creating the square is just a fancy way of saying making an array or using the area model.
Now I want to fill this in based on what I get when I multiply my factors here. So I have x times x, positive x equals x positive x squared. I have x times negative 1. I have negative 1 times x, 4 times. Okay, and then I have negative 1 times a negative 1, which is positive. Okay, so my answer to this should come in the sum of all these parts here. So if I add them all up, I should have x squared. I have negative 5x plus 4. Okay.
Could you slide your paper slightly to the left, Chris?
There we go.
Thank you.
Okay, so same thing. We're going to build the factors on the outside. X plus 3 and x and a negative 2. So those are my factors. Now I want to build my middle here. X times x, x times 1, times 1, times 1, negative 1 times x, a negative 1 times a positive 1. Times. So my answer comes in here. I should have x squared. I can 0 pair out 2 of these, and I get x and a negative 6. All right, the last one, let's go to factoring. Let's try this one. So this time, I'm just going to bring in the pieces that I have here. I have x squared. I have 5x. And I have a positive 6. And my goal is to create a square with what I have here. Okay, so if I line these up down here, doesn't quite work. I'm missing something right there. If I were to move one of these over here, kind of works, but I'm missing something here.
You're trying to make a perfect rectangle, right? So that we have an array.
I'm going to keep moving. Oh, look at this. There we go. Now, to get my factors, I need to look at the top edge and the side edge here. Okay, so my factors become an x at the top edge here. This is the x. And then I have 3 units right there. Okay, so x plus 3 and x plus 2. Let's try another one. So I'm just going to bring in what I have there. An x squared, 1x, and a negative 6. And I'm trying to complete a square with it. Okay, so I can do that. I can do this. I already see this is going to be an issue. Okay, I can line them up like that. All right, but, weird. But we know that bringing something like that in a zero pair, I can bring it in and it's not adding anything. It's not adding any value to this. So what if I tried to bring in a zero pair to complete this? Can I do it again? All right. So now my answer comes right up here. I should have x plus 3. So an x plus 3 and an x minus 2. All right.
The algebra tiles are so powerful in the classroom, and I love that we can actually touch them and move them around. There are times when students might have access to a Chromebook or some online they may have something that they can go online with, or perhaps they're at home and they don't have algebra tiles to work with. A lot of companies have virtual algebra tiles out there. This happens to be from one of the resources, high school textbooks. It's CPM's website, and they have a whole algebra tile section. Just wanted to show you how this might work.
This is a free resource, right, Sarah?
This is a free resource, yes. You can drag the algebra tiles that you need from the side to build your expression or equation.
Can you copy?
You can. So for example, let's say I want another 2. I didn't do that well. If I want another 2, I can copy them.
Control C and then Control V.
Sorry, just can't get it at the moment, but yes, you can copy a group of them to make it go faster if you want to. To make them negative, you simply tap on, touch them once and they will go negative or positive. And if you tap them twice, they will turn. So if you wanted to build a square, you could do that as well. We just wanted to point these out because these would be great. The virtual manipulatives would be great in the classroom, or they would be great at home when our students are safer at home.
Sarah, I see there's some Y's on there.
There are. This set of virtual tiles comes with a y and a y squared. Also comes with that xy. So lots of possibilities. You can really take this up into the upper level algebra courses. So with that said, we really want to thank you all for joining us today. We hope that you found something that you can take to your classroom or take to your students as they're safer at home. Please follow us on our CESA 6 social media platforms. We would love to put out other tips and hopefully find some things, hopefully you'll find some things that would be helpful to you. So thank you so much for everything that you're doing for our students during this time. And you are truly keeping us at CESA 6 moving because we are just so inspired by everything that you're doing. Chris, thank you for all your hard work today, and we hope to see you in the next webinar.
Thank you.